Hey everyone, welcome. I am so excited you're joining us today. So, for this explainer, we're really focusing squarely on explaining the chapter's core concepts, but we're going to do it by turning a standard math lesson into, well, kind of a thrilling detective journey. We're going to uncover the hidden rules of the fraction universe using everyday, mouth-watering stuff like chocolate bars and soft, warm parathas. And honestly, whether you're completely new to this or just looking to solidify what you already know, we're going to break the whole logic down step by step.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the chocolate paradox, then playing with grids, move on to the magic of equivalence, and finally wrap up with fractions greater than 1.
All right, part one, the chocolate paradox, which is really all about the rule of the whole. To really grasp this first rule, let's look at a real-world scenario with Tamana. She's a fifth-grade student with a pretty serious sweet tooth. Now, I want you to pause and just think about this for a second. Can 1/3 of a chocolate ever be bigger than 1/2 of a chocolate? I mean, all our basic math instincts immediately scream no way, right? We're always taught that a half is fundamentally larger than a third. But Tamana is out here claiming her 1/3 piece is bigger than her friend's 1/2 piece. How could that possibly be true? Well, the crazy thing is, Tamana is absolutely right. Why? Because she's dealing with two completely different sizes of chocolate to begin with. If you look at it, 1/3 of a massive chocolate bar is physically going to be way larger than 1/2 of a tiny little 4-piece bar. The fraction by itself, it doesn't actually tell you the physical size of the piece. It only tells you its relationship to whatever object you started with. And honestly, that brings us right to the first golden rule of the fraction universe, straight out of the chapter. To compare two fractions of two wholes, the wholes from which the fractions are derived must be the same. Basically, if you try to compare a fraction of a tiny whole to a fraction of a giant whole, the numbers are just going to deceive you. The baseline, the whole itself, has to be identical if you want a direct comparison to actually work. Moving right along to part two, playing with grids. Let's start comparing these fractions. Okay, now that we've established our first rule, let's transition from physical chocolates into a more abstract space to really put this to the test. Imagine you have 3 blank grids, and they are identical in size, so our holes are now exactly the same. But they're divided up differently inside. Grid A is chopped into 8 parts, grid B into 6 parts, and grid C into 12 parts. If we shade 1/8 of A in red, 1/6 of B in blue, and 1/12 of C in yellow, we're dealing with different fragment sizes. But because the total grid sizes are exactly the same, we can confidently say, yep, that blue 1/6 piece is definitely larger than the yellow 1/12 piece. But let me challenge you to play a detective for a minute. If you were staring at those grids divided into sixths or twelfths, do you see a 1/3 hiding anywhere in there? Well, if a grid is divided into 6 equal rows and you shade 2 of those rows, you've just shaded exactly 1/3 of the whole grid. See, it was hiding right there in plain sight. Which brings us beautifully to section 3, the magic of equivalence, or the disguise. So that hidden 1/3 leads us perfectly into our next core concept in explaining the chapter. This is the part where fractions basically put on a trench coat and a fake mustache and pretend to be entirely different numbers. The crucial point here is understanding what this disguise actually is. We call them equivalent fractions, and the textbook definition is actually really helpful here. They are simply two different ways to write the fraction represented by the exact same shaded part. So they might look totally different on paper, different numerators, different denominators, but they hold the exact same real-world value. Think of it like this. Gupri is playing with his fraction kit to figure this out hands-on. He starts with one big 1/2 piece. Then, he snaps that 1/2 piece right down the middle into 2 equal parts. He instantly notices that each of those new, smaller parts is exactly a 1/4 piece. And when he pushes them back together, it's super obvious that 2 1/4 pieces take up the exact same amount of space as the original 1/2 piece. The pieces got smaller, sure, but he doubled how many he had, so the overall value literally never changed. And this perfectly illustrates our earlier detective work with the grids. 1/3 is identical in value to 2/6. Think about pizza. If you have a pizza cut into 3 massive slices and you eat 1, or you have a pizza cut into 6 slices and you eat 2, your stomach is going to be equally full. They are mathematically equivalent. What this really means is that 1/2 isn't just a static, boring number. It is a gateway to this massive, infinite universe of equivalent fractions.
1/2 is 2/4. It's 3/6. It's 4/8, 5/10, the whole shebang. As long as you multiply the top number and the bottom number by the exact same amount, you are just slapping a new disguise on the very same fraction.
All right, let's move to our final act. Section 4, fractions greater than 1. Breaking the barrier.
Up until now, we've only been talking about parts of a single whole. But what happens when we're really hungry and we outgrow that single whole? To ground this abstract math back into mouth-watering reality, let's step back into the kitchen. Raman's father is making these incredibly nice, soft parathas for a family dinner. And before he serves them, he cuts every single paratha right down the middle, perfectly into halves.
Now, at the dinner table, Raman realizes his ma ate 5 of those half pieces. When you write that down mathematically, you get this weird top-heavy looking number, 5/2, 5 halves. We call this an improper fraction, and frankly, it looks super intimidating. I mean, how can you have 5 parts of something that's only divided into 2? Okay, let's just logically step through this conversion so it doesn't seem so weird. Ma ate 5 pieces, right? And every single piece is a half. Well, from our earlier rules, we know that every 2 halves snap together to make 1 whole paratha. So 4 of those halves combine perfectly to make 2 whole round parathas, and that leaves exactly 1 half piece sitting by itself on the plate. So 5/2 is literally the exact same thing as saying 2 whole parathas and 1 half paratha. Suddenly the math makes total intuitive sense.
As we wrap up this explainer, I want to bring us right back to square one, just to really cement the absolute core takeaway of this chapter. To compare 2 fractions of 2 wholes, the wholes from which the fractions are derived must be the same. Whether you are comparing chocolate bars, grids, or slices of parathas, the context of the whole is literally the master key that unlocks this entire fraction universe. Because, fractions aren't just numbers trapped in a textbook. They're actually the hidden language of the shapes and spaces all around us, every single day. So here's my final question for you. Next time you sit down for a meal, whether it's a pizza, a paratha, or just a chocolate bar, can you play detective and spot the hidden equivalent fractions right there on your plate? Thank you so much for exploring this with me today, and keep looking for the math around you.